Hello everyone, today let's solve the problem number 1 to 4, binary tree maximum path sum. So what the question states here, we are given a binary tree. So you can clearly see we are given a binary tree, right? So we are given an binary tree here. We have to, we are given a binary tree, sorry. We have to find the maximum path sum of any non-empty path. So they have clearly mentioned here, we have to find the maximum path sum of any non-empty path. This is very important. A path consists of connected nodes and it doesn't need to pass through the root. A path consists of connected nodes, right? So a path consists of connected nodes and it doesn't need to pass through the root, and there is no such condition that it has to pass through the root itself, right? So a path consists of the connected nodes and it doesn't need to pass through the root. So that's what they have given in the question here, right? So let's come to the first example here. Just give me a second here. Yeah, 1 second. Yeah, so here you can clearly see we have been given a root 1, 2, 3. We have 1, 2 and 3, right? Root, left subtree as well as the right subtree. So here they have given the output is 6 because 3 plus 2 plus 1, 1 plus 2 plus 3 is nothing but the 6. So the optimal path 2, 1, 3, this one they are speaking of 2, 1 and 3, right? So the optimal path is 2, 1, 3 with a path sum of 2 value they are considering, right? 2 plus 1 plus 3, nothing but 6 in this case. So this will be the output in this case, right? So let's come to the second example. Easy to understand this one, the first one. So let's come to the second example here. So here in this case the optimal path is 15, 20 as well as 7, right? So you can just take this path, but it will be 9 minus 10, 20, right? So 29 minus 10 will be 19 in this case, right? So you can just consider, you can just try this path 15, 20, 7 in this case, right? 15, 20, 7. So when we try for 15, 27, it will be 20 plus 15, 35, 35 plus 7 is 42. So we can just consider this path, considering this as root, right? So 20. So this one as root. So the optimal path here is 15, 27 with a path sum of 15 plus 20 plus 7 in this case, right? 42. It will be 15 plus 20, nothing but 35. 35 plus 7 is nothing but in this case 42. So in this case it will be 15 plus 20 plus 7, right? So 20 plus 15 is 35, 35 plus 7 is nothing but 42 in this case, right? So 42 will be the output that we need to return in this case. So just, yeah, so this is 42. So the optimal path here is 15, 27 with a path sum of 15 plus 20 plus 7 is 42. 14 equals 7 equals 42, sorry. Yeah, now I hope the question is completely clear. What we need to do is completely clear. We need to check the path as we have to keep one element as a root element, right? So we need to check every path and we need to go with we need to return the path that is maximum. Means the path sum of the path is the sum of the nodes value in the path they have given here. The path sum of a path is the sum of nodes value in the path they have clearly mentioned here, right? So we have to return the maximum path sum of any non-empty path. So in this case we have seen how we got the output already, right? So I hope the question is completely clear. What we need to do is completely clear as well. So let me clean up this one. So let me clean up this one here. So I'll just come here in this case. First let's discuss the approach, then followed by the edge cases, and then finally write the code and discuss the complexities for the code that we have written. Initially let's discuss the approach first. So the first thing that we need to note down here is we are going with the recursive DFS with backtracking. So this is the approach that we will be going with, recursive backtracking with, recursive DFS with backtracking. This is fine. I have considered the first example that they have given in the example so that it will be easier. We have already considered this one, right? So this will be 2 plus 1 plus 3. This is the maximum path we have to get. So in this case 2 plus 1 is 3, 3 plus 3 is 6. So we have already discussed this one. We have idea on this one, right? So let's move on with the step-by-step execution here. So same example that I have considered here, root equals 1, 2, 3. So you can just, so I'll just show you the approach for the example 1. You can just try it out in the same way for the example 2, or you can just try it out with the different numbers by drawing the tree, right? So you can just do the same thing. I insist you to do the same because you'll understand that this one approach better, right? Your might be your way of writing the code is different, so might be you'll get to know something that I haven't said here. So just I insist you to do the same thing, to try out with the different examples, right? So let's come to the first thing here. So here we are going with the recursive computation right here. So we are going with the mainly the approach that we are going with here is recursive DFS with backtracking. So the first, this one here is first step here, that is we will start from the root 1. So here the diagram I'll just give you 1 2 3. We will go with the, we will start with the root 1 here in this case, right? We will start with the root 1, and also we will calculate the max path sum for left 2 as well as the right 3. This I'm speaking of, right? So this one. So first we'll start from root 1 and we'll calculate the maximum path sum for left 2 and right 3. Let's move on with the second step here. So first thing here is we have to find the max path of 2. So left and right subchildren are null. Here this one I'm speaking of. This doesn't have left and right subchildren, right? So this one is null in this case. So are null. So the maximum sum is 0 here in this case. So this would be for the left 2 plus 0 plus 0, because we don't have any this one children for the 2. So this will be 2 itself, right? So this is first step. Let's move on with the next step here. Find max path of 3. So left and right children are null as well for this as well. So their maximum are 0. So this one I'm speaking of. So here also we don't have left and right subchildren. This will be 3 plus 0 plus 0. In this case, this will be 3 as well, right? This doesn't have children, right? So for this one also it would be 3. So another path we got here is this one. What do we call? 3. For first path we got 2. For the second path we got this one 3, and the final path here is find max path of 1. For 1 also we have to find the max path here, right? This one I'm speaking of. 1, just give me a second here. This one. So we didn't find the max path. First we found out that this one is having left and right subtree. We are finding this path basically. Both are having null, so this one will be 2, this one will be 3. Now we have to find the maximum path for 1. So let me come here. This one I'm speaking of. When I say maximum path of 1 here, 1 is having the children 2 and 3. So this will be 1 plus 2 plus 3, right? So this will be 1 plus 2 plus 3, which will lead us to 3 plus 2 5. 5 plus 1 is nothing but 6, which will lead us to the 6, right? So 6 is the solution. Out of this one we will find the max. Basically out of 6, 2 and 3, maximum is 6. So the maximum path is this one 1, 2 and 3, or 2, 1 and 3 you can consider. In example we consider it in a in order way, right? 2 plus 1 plus 3. So in order we considered. So in this case it will be 6. The max of 6, this one 6, 2 and 3 is quite obviously 6, and the path is here 2, 1, 3, right? So this is fine. So here let me come here. In this case current max is 1 plus 2 plus 3 is nothing but 6. Final maximum we got out of all the paths is 6. We considered all the sum, right, from different paths basically, out of which 6 was the max sum. So we have to return 6 in that 6. We have to return 6 as output. So this is how we got 6 as output. We got 6 as output, which is equivalent to the output that they have given for the first example in the question, which is same. Here 6. 6 is equivalent to 6. So the approach works absolutely correct in this case. As we are familiar with the approach, let's discuss the edge cases one by one. So the first thing here is the first thing we have to discuss for here is we have to discuss for the single node tree. Sorry. So we have to discuss for the single node tree. Here we have only one node 5. So we will return output as 5. So this is the maximum path, right? Only root node we have. In this case, it will be 5. So all the negative nodes. Let's move on with the second edge case here. This is for the all negative nodes. Root we have. So the elements we have here as -2, -1 and -3. So the output will be -1. So least one. So the path you can just draw the diagram and you can do the exact same thing I had showed for the example I had showed by considering the example 1 in the question. So the same thing we did for the approach, right? You can just consider the same example, this example, and you can try it out in the same way that I showed for the example 1. You'll understand this one clearly. I insist you to do this one with the second one, right? So let's move on with the third edge case here, tree with zeros. We have 0, 1, 2. So the maximum path sum is here, it is 3. So let's move on with the fourth edge case, tree with the mixed values. You can see here mixed values means we have null, we have negative value, we have positive value as well here, right? In this case the maximum path sum is 42, right? So the maximum path sum is 42 here in this case. So these are the edge cases that we need to keep in mind. The first edge case is for the single node tree, the second edge case is for the all negative nodes, the third edge case is for the tree with zeros, and the fourth edge case is for the tree with mixed values. So these are the 4 edge cases that we need to consider, right? So now we are completely familiar with the approach, as well as now we are completely familiar with the edge cases as well. As we are familiar with the approach and the edge cases, it will be easier to write the code. Let's start writing the code. So now let's start writing the code. Initially, so we know that we have to store the maximum path sum, right? So we need to have certain variable for it. So I'll just consider here private int. So I'll just go with max sum here. This is fine. So the next step here is, so I'll just write this one before this one. So just give me a second here. Let me cut this one. Let me paste it over here. Format this one once. So yeah. Sorry, just give me a second here. This is fine. So the first step within the main function here is, so we have to initialize the maximum sum with lowest possible value, right? So I'll just go with the integer.min value for that one. So we have already considered the variable max sum, right? So I just don't have to mention the data type here. So I'll just go with here integer.min value. This is fine. So the next step after initializing the max sum with the lowest possible value, we have to start the recursive DFS traversal. We have to start the recursion, right? So we have to start the recursive DFS traversal here. So for that one, so we will be making use of the max path sum, right? So we will be making use of the helper function max path sum. So we haven't written that one yet. So let's do that one first, and then let's make use of that one here within the main function, right? So I'll just go with private int. So I'll just go with find max path, right? So find max path. Let me make this M capital here, right? This is fine. So I'll just go with the parameter node here. So I'll just go with here node. This is fine. So base case, if you remember, so we have already discussed this one. If node is null, then we have to return 0, as it contributes nothing. It doesn't contribute anything, right here. If node is null, then we have to return 0 in that case. So I'll just go with here, if node equals null, then what I'll do here in this case, let me return 0. This is fine. So the next step here is, we have to get the maximum sum from the left subtree as well as the right subtree, right? So this was our first step. We have to get the maximum sum from the left and right subtree. So this is what we have discussed clearly step by step in the approach. That's what we'll be doing here. Let's articulate the same thing in the form of code here. So this will be left max equals math.max. So we have to get the maximum sum from the left and right subtree. First, let's find the maximum sum from the left subtree here. This will be 0, find max path. So I'll be making use of the function here, recursive function. Find max path of node dot left. This is fine. I hope this is fine. So the next thing, I'll do the same thing with for the right subtree as well. So let me copy the same thing here. Instead of left max, we will be going with the right max this time, right? So this is fine. So instead of node dot left, I'll just give here node dot right. So I hope this is clear, simple to understand, right? So the next step is, we have to compute the sum of the path that is passing through the current node. Quite obviously, we have to compute the sum. That's what they have asked in the question to do, right? So we have to compute the sum of every path, and we have to finally return the maximum path sum. So we have to compute the sum of the path that is passing through the current node. So we have to articulate the same thing, the logical thinking, the process, right? So that we had discussed in the form of code here. So I'll just go with here int current max. So I'll just give here, it will be value of the node plus left subtree and the right subtree, nothing but here in this case we have considered this one variables left max and right max, right? So I'll just copy the same thing here. This one I would have done same thing for the left max as well. This is fine. So after this step we have to update the maximum sum if the new path is greater. So whenever we find the new path, the new path sum is greater, we have to update the max path sum. And for the first example we got three this one, right? Path sum, we got three path sum, out of which we updated the maximum path sum every time, right? So finally we returned 6 as output because it was the max path sum, right? So that's what we need to articulate the same thing in the form of code here. So I'll just write here max sum equals math.max of max sum current max. This is fine. The final step here is we have to return the best sum that includes the current node. We have to return the best sum that includes the current node. So I'll just go with return value of the node plus this one will be math.max of I'll consider this one left subtree as well as the right subtree. This will be left max plus right max. This is left max and right max if we had this one. So we are performing DFS, right? So this will calculate for entire left. So when I say entire left, so we will calculate the entire thing for this one. So we'll calculate entire thing for the right here. This one, entire thing. That's what I'm speaking of, right? So just give me a second here in this case. So what I'll just copy this one and paste it over here, right max. This is fine. So finally we return the best sum that includes the current node. Best sum means the maximum sum, right? So this is fine. So now let's come to the main function here. Within the main function we have to start the recursive DFS traversal, right? So we have to, in the next step we have to return the highest path sum that is found. Before that one we have to start the recursive DFS traversal. Now we have already made use of the helper function find max path. We have completed writing this one code within that function. Now we can just make use of the this find max path function within the main function for to perform the recursion or to perform recursive DFS, right? So here I'll just paste the function name here, find max path of root. From the root we have to carry on, right? So this is fine. The final step is we know this one. We have to return the highest path sum that is found, right? So let me go with return max sum. Simple. So here let me format the code once. Yeah. Now we know this one, right? So now we are completely familiar with the code that we have written. So let me hit the run button. So I hope this works. Let's see. So we have some error. So MA has to be small here. Where is this? Line number 20. So here let me make this A small. Let me run the code again. Let me hit the run button again. So here you can clearly see the sample test cases are getting passed. Means the code works absolutely correct on this case. Let's see whether this works for all the test cases or not. Let me hit the submit button. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct on this case, right? So let's quickly discuss the complexities for the code that we have written. So initially, the first thing that we need to note down here is, means the approach that we went with here is recursive depth first search. Means recursive DFS with backtracking, right? So this one is recursive depth first search, recursive DFS with backtracking. So overall time complexity would be big O of n, right? So the overall time complexity would be big O of n. So what would be the space complexity here? The overall space complexity would be big O of h. So why the time complexity here is big O of n? Because we are visiting the each node once in a post order manner, right? So we are visiting this one. We are visiting each node once in a post order manner, right? So we know this. And also, why the space complexity is big of h here? So in the worst case, it is big of n for the skewed tree, we know, and we are making use of the recursion stack depth, which is at most the height of the tree, nothing but h in this case. So I have written here big of h, right? So the time complexity is big of n and the space complexity is big of h for the code that we have written, right? So I hope the complexities are clear, and I hope whatever the code that we have written is completely clear as well, right? For now, this is it. Thanks for watching, guys.